policy gradients, they use these cool tricks to estimate the gradients and update the parameters.
Sounds like some serious math is happening.
Oh yeah, and these algorithms are responsible for some of the biggest achievements in RL.
Like AI mastering Go.
Yeah, we've covered a lot of ground, from the basics to some of these advanced techniques, but how does all this connect to more traditional approaches to control?
Yeah, there's got to be some overlap, right?
You're right, there's a fascinating connection between RL and optimal control theory.
Optimal control theory. Tell me more. Okay, optimal control theory. That sounds pretty textbooky. Can you give me the short version?
Sure. So it's basically about finding the absolute best way to control a system over time, to hit some specific goal. It's like designing the perfect autopilot system for an airplane or figuring out the best way to control a robot arm in a factory.
So still about optimization, but from a more traditional engineering perspective.
Exactly. And it might seem completely separate from AI and all that,
It does.
but there are actually some pretty deep connections between optimal control theory and reinforcement learning.
Oh, that's interesting. How do they relate to each other then?
Well, in both cases, we're looking at systems that change over time, right?
Right.
And we're trying to find a strategy that maximizes performance. So in optimal control, you're finding the best way to kind of steer the system to get to a desired state. In RL, you're finding the best policy to guide the agent and maximize rewards.
So both are tackling this optimization problem, but using different methods.
Precisely. One key concept in optimal control theory is this thing called the Hamilton-Jacobi-Bellman equation.
The what equation?
Yeah, it's a mouthful. The HJB equation.
Okay, the HJB equation. Got it.
It's this mathematical equation that describes the best possible value function for a control problem.
Hold on, the value function. Like how good it is to be in a particular state. That sounds just like reinforcement learning.
Right, you're getting it. The HJB equation lets you calculate the value function and figure out the best way to control the system. And here's where it gets really cool. The HJB equation is actually closely related to Bellman's equation.
The one that describes the relationship for the value function. So they're both talking about the same basic idea?
They are. It's like Bellman's equation is a simplified version of the HJB equation for specific situations. This just highlights how closely connected RL and optimal control theory are.
That's amazing. So is it fair to say then that reinforcement learning is a more modern approach to these classic optimal control problems?
Yeah, in a way, yeah. It's a super powerful framework, especially when traditional methods have trouble. Like when you don't have a perfect model of the system,
Right.
or when the environment is just super complex or unpredictable. That's when RL shines.
Because it can learn as it goes.
Yeah.
Without needing all the instructions.
Exactly. And that actually leads us to this really cutting edge area of research that combines the power of deep learning with optimal control, deep model predictive control, or deep MPC.
Deep MPC. Okay. What's that all about?
So deep MPC uses deep neural networks
Of course.
to learn those complex models from data, and then it uses those models to plan and make the best control decisions. It's like having an AI controller that can actually predict the future.
Wow. So it's like an autopilot, but it anticipates what's coming next and makes adjustments ahead of time.
Exactly, and it's showing some incredible potential. We're talking robots that can move with more agility, self-driving cars that navigate tricky traffic more safely, and even systems that can optimize energy use in power grids.
This is also incredible. We've come a long way from the basic ideas of reinforcement learning to this really advanced research, but I feel like we're just scratching the surface. What's next for RL? What are the big questions that researchers are working on?
You're right, it's just the beginning. RL is growing so fast and has so much potential. I think one of the most exciting areas is how it can be used to solve real-world problems. Those messy, unpredictable scenarios where the goals are always changing. Things like climate change, or personalized medicine, or building smarter cities.
Those are huge challenges, and RL could really help find solutions.
It really could. As you continue learning about this field, here's something to think about. We've seen that RL agents can master games. Games have clear rules and goals. But can these agents handle the complexity of the real world when things are more ambiguous and the stakes are so much higher?
That's a great question. It really makes you think. Well, that's all the time we have for today's deep dive into the world of reinforcement learning.
It was a fascinating discussion.
It was. To our listeners, we hope this has sparked your curiosity. If you want to delve even deeper, there are lots of resources available online. You can connect with experts in the field and keep asking those thought-provoking questions. The future of AI is unfolding right now, and your interest and insights are a crucial part of this journey. Thanks for joining us.